Hello and welcome to the discussion on Fourier transforms. But before we go into the mathematical aspect of Fourier transforms, looking at the examples and the formulae, let's first appreciate Fourier transforms and the reason why Fourier transforms exist. In order to do that, let's take the example of something that all of you are fond of during the hot summer months, the example of smoothies. We all enjoy a cup of smoothie when the weather is hot outside. But how many of you will be able to recreate a smoothie at home? Well, if you knew the ingredients of a smoothie, then it would be easy to recreate it, isn't it? Now imagine a world before the internet. How would you get the recipe of a smoothie? Well, this is a challenge which is very similar to a challenge that many mathematicians face when they are given with a complicated equation of a signal. This equation here is a complicated example of a signal. Now this signal is comprised of many independent signals, just like how a smoothie is comprised of many independent ingredients. Together all those ingredients form a smoothie. Together many simple waves combine to form a complicated signal. Now in order to recreate this signal, mathematicians have to break this into independent signals, just like how you would have to break this smoothie into independent ingredients in order to recreate it. So let's try to enjoy Fourier transforms just like how we enjoy smoothies, and let's try to understand what Fourier transform does to this complicated looking signal. Suppose you have a smoothie which is composed of strawberry, milk, water, banana and sugar. Now how do you get the ingredients? Suppose you had filters, hypothetically, filters which separate out different ingredients of the smoothie. So if you run the smoothie through these filters, it will give you the exact quantity of strawberry, the exact quantity of milk, the exact quantity of water, the exact quantity of banana, and if there is sugar, the exact quantity of sugar. Now you know how much strawberry went into the smoothie, how much milk went into the smoothie, how much water went into the smoothie, how much banana and sugar went into the smoothie. How do you recreate the smoothie now? Combine all of these things and you get the smoothie back. So these filters are like Fourier transformation of a complicated signal. A Fourier transformation of a complicated signal breaks the signal down into its simple individual component waves. So you get to know what are the simple waves which are present in that particular complicated signal. Then what do? In order to recreate the signal, you merge all of them, and that is what inverse Fourier transformation does. So once you have the filters, you can break the smoothie down into its individual components and then mix all of them up to get the smoothie again. Now there are some interesting components of these filters which need to be satisfied in order for these filters to be effective. The first thing is these filters must be independent. A strawberry filter should tell you the quantity of strawberries only. It should not tell you the quantity of milk. Then you're actually losing out how much strawberry do you have, because you're going to get a mixture. So each Fourier transform filter should tell you about only one wave and not a mixture of waves. The second thing is these filters must be complete. They should not give you half information about how much strawberry is present, then it beats the point of that filter. So your Fourier transform should be able to describe each component waves completely and not partially. And finally, after doing a filtering, you should be able to recombine to get the smoothie. Otherwise the whole point of filtering is lost, because you want to recreate a smoothie. Similarly, you should be able to invert the Fourier transformation so that you can merge all of the individual component waves to obtain the complex signal. So let's now look at Fourier transformation from a signal point of view. So there is a signal here, and this is not an easy signal. This signal is quite a complex signal, and if you have to recreate this signal, you have to break it. And suppose this signal is composed of three signals, the red one and the green one and the gray one. Fourier transforms will split this wave out into 3 different waves and give you the components of all of these things. So you've got all the individual components. If you merge these things, you will get the complete wave again. Now you might be wondering, what is the point of breaking a complex wave into individual waves? Well, there are a lot of applications to this. The entire domain of signal processing actually deals with this. And one example which stands out is noise cancellation. Suppose this green wave here is noise and you want to remove this noise from this. Unless and until you get the components, you will not be able to remove it. So what you do is you get your wave, you get all the components, you identify the noise, and then cancel this noise out. Just combine these two people and you get a signal which is devoid of noise. You want an application of this? A very famous application of this happened during the Football World Cup of 2010, which happened in South Africa. A very popular noise during this World Cup was the noise of vuvuzelas. These vuvuzelas were horn-like objects which created a deafening noise in the stadiums, and that created an amazing atmosphere in the stadium. But this posed a challenge to the broadcasters, because during broadcasting, these vuvuzelas were very disturbing to the audience who were viewing the match on a TV set. So the broadcasters were faced with a challenge of removing the noise that the vuvuzelas created when they broadcasted these matches live worldwide. So what they did was they applied a Fourier transform to the noise which was coming out of the stadiums and then removed the noise of vuvuzelas, and then they did an inverse Fourier transform and sent out the deafening noise which was there in the stadium minus the vuvuzelas. Now the stadium had an amazing atmosphere because of vuvuzelas, and people who were sitting at home did not have to listen to this harsh voice which was not broadcasted. So this is the amazing effect of Fourier transforms and noise cancellation, an amazing application of Fourier transforms in the world of broadcasting. Another great application of Fourier transforms is when you want to do some sort of noise processing or voice modulations. For example, if you have a rock and a pop concert happening, if you want to identify the nature of the frequencies which are present in a pop concert and in a rock concert, you can actually apply Fourier transforms and you can identify the different frequencies which are present in a pop concert and a rock concert. So in the world of noise, in the world of music and sound, Fourier transform has amazing applications. So for all of you who are interested in signal processing and who want to do digital signal processing, and the ones who are really going to be interested in communications, you are going to need Fourier transforms a lot in your careers. So welcome to this beautiful world of Fourier transforms, where signals can be processed and noise can be removed, and you can produce beautiful sounds out of anything that you get. Fourier transforms have great application in the world of signal processing, and let's look at the mathematical aspect of Fourier transform in this chapter, and in the future lectures we're going to look at all the different formulae that help you split out signals into their component waves. Welcome to Fourier transforms.